machines. And it is the ability of machines to automatically learn without being explicitly programmed. And that is actually another definition of machine learning: the ability of machines to automatically learn. And this learning is actually happening from the prior experience, or from the data available in our machine. And this learning is actually without being explicitly programmed, without writing any type of a program, or without, as in the case of our Java or C++, without writing a program for explicitly doing a particular task. From in order to learn the information contained in the data set, we can explicitly, without being explicitly programmed, we can perform this task. And the origin of machine learning, and that is actually traced back to 1957, when the concept of perceptron model was introduced. There is Rosenbolt introduced the perceptron model in 1957, and after that we can see that there was a sudden change in the concept of machine learning algorithms. A drastic change occurred after this 1957. And you know, perceptron, that is a device that makes decisions by weighing up evidence, and that term is also very important. Evidence, actually, that is data. Weighing up evidence means this data is represented with the help of features. Okay, these features we can provide, or we can give different weights to these features for representing the significance of these features for taking the decision. And that is the meaning of the last statement, that is weighing up evidence. And this is the general structure of an artificial neuron. There is here we can see that there are a number of different components are there: x1, x2, x3, etc., xn, w1, w2, w3, etc., wn. Then another very important component, that is the summation operator and the activation function. And the output of this activation becomes the output of the neuron. And this is the general architecture of an artificial neuron. And in this architecture, or this configuration, is called a perceptron. And the inputs x1, x2, x3, etc., xn, and the weights w1, w2, w3, etc., wn are real numbers and can be positive or negative. Okay, and the perceptron consists of weights, that is w1, w2, w3, etc. And here w1 is actually the weight associated with the first input, that is x1, or first feature x1. w2, that is the weight associated with the second feature. w3, that is the weight associated with the third feature, etc. wn, that is the weight associated with the nth feature. That means all the features are individually weighted. And the perceptron consists of weights, summation processor, and an activation function, And these are the three very important components of a perceptron. And summation processor, the responsibility of this summation processor is that it computes the quantity, that is w1 x1 plus w2 x2 plus etc plus wn xn. And for computing that information, we can make use of the summation processor. And the output of the summation processor is given to the activation function. And a number of different activation functions are there. We will discuss later. And when we provide the output generated by the summation processor to this activation function will generate an output. And that output becomes the output of that perceptron. Okay, and that is the working of a perceptron model. And in this particular perceptron model, all inputs are individually weighted, added together, individually weighted, added together, and passed to the activation function. That is, we can compute W1x1 plus W2x2 plus etc. plus Wnxn, and this quantity is passed to the activation function. And the simplest activation function is a step function. And this step function output a 1 if the input means that is the output generated by the summation operator, and that input is greater than t, a threshold value, then in that case the activation function generates a 1 output, otherwise its output will be 0. So these are the only 2 outputs generated by a step function. And some other activation functions are also there, like sigmoid activation function, then ReLU activation function, leaky ReLU activation function, then Tanach activation function. A number of activation functions are there, and a selection of a particular activation function is based on the where we are going to apply the concept of this artificial neuron, in which domain. Based on that domain, we can select the appropriate activation function. Next, we can move on to the multi-layered neural networks. Then a multi-layered neural network, and also called the multi-layer perceptron, is composed of one input layer, one or more hidden layers, and one final layer called the output layer. So a multi-layer perceptron consists of different layers of neurons. The first layer is called the input layer. The second layer is called the hidden layer, and the one final layer, and that is called the output layer. Then, when an artificial neural network or multi-layer perceptron has 2 or more hidden layers, it is called the deep neural network. That means in a particular multi-layer perceptron architecture, we can expect a number of hidden layers. If the number of hidden layers, that is 2 or more hidden layers are there, then such type of an architecture, and that is known as a deep neural network. And when we consider a multi-layer perceptron or a deep neural network, the information flow in that multi-layer perceptron occurs in this format. That is, first we can provide the input to the input layer, and from that input layer, the information move on to the hidden layer. Then from the hidden layer, it goes to the output layer, and in the output layer, or it is the responsibility of the output layer to generate the required output for the neural network. So in an MLP, in a multi-layer perceptron, usually multiple hidden layers are there. Each layer may contain any number of nodes. Any number of nodes are there. Any number of perceptrons are there. And the number of classes that determines the number of nodes in the output layer. So how many nodes are there in the output layer? And that is actually decided by how many outputs we have to generate, or in the case of a classification problem, and if the classification problem is a 2-class problem, then in the output layer we can expect 2 neurons. And if the problem is a 3-class problem, and in the output layer we can expect 3 neurons. But in the hidden layer we can insert any number of neurons. There is no restrictions. We can use any number of hidden layers. Okay, and that is the information with a multi-layer perceptron. And in order to use this multi-layer perceptron efficiently, we have to use an algorithm for updating the weights of that network. I think all of you know, every inputs are associated with some weights, and the appropriate value for these weights, that is W1, W2, W3, etc., Wn, actually determines the performance of that particular multi-layer perceptron. So tuning the weights, and that is a very important criteria in a multi-layer perceptron model. So a learning algorithm in multi-layer perceptron actually tune the weights between the output layer and the hidden layer, That means in between each layer, we can expect some weight values. So this learning algorithm actually tuned the weights between the output layer and the hidden layer, and the weights between the hidden layer and the input layer. So in between input layer and the first hidden layer, we can expect a number of weight values. Then tune these weights, and that is the main objective behind the learning algorithm of multi-layer perceptron. And the method used for tuning the weights, and that is take the errors at the output layer. That means in the output layer, when we provide a particular input in the input layer corresponding to that particular input, at the output layer, the multi-layer perceptron generates an output. And based on that output and the actual output, we can compute the error. And after computing that error, using gradient descent, and that is the learning algorithm used in the multi-layer perceptron for tuning the weights. By using gradient descent, proportionally propagate error backwards to the hidden layers. And the gradient descent, that is very important. I think all of you are familiar with the concept of gradient. Gradient is nothing but the derivative. For example, if you consider a function y is equal to f of x, then what is the derivative? First derivative of that function is dy by dx. That is the rate of change of y with respect to x, and that is the gradient. And the same concept can be applied here to generate the or to modify the weight values or tune the weight values. That means these weights are modified with respect to the error generated. So if the weight is w, then error is e, then this rate of change is nothing but dw divided by dw by de. That is derivative of weight with or rate of change of weight with respect to the error generated. And that concept is used in multi-layer perceptron for tuning the weights lies in between the input layer and the first hidden layer. Okay. And this is the simple architecture of a multi-layer perceptron model. And this is the input layer. Then from this input layer, the information flows to the hidden layer. Okay, and in this hidden layer, any number of neurons we can include. Then this is the final layer, and that is the output layer. So information from input layer is flows to the hidden layer, and from the hidden layer it goes to the output layer, and in the output layer we can generate the required output. So here this is an example for a 3-class problem. The information or the numeric value generated in the first neuron of the output layer determines the involvement of the particular input corresponding to the first class. Then here we get another value, and that is the involvement of the input values corresponding to the second class, and so on. Okay, and therefore this is the simplest architecture of a multi-layer perceptron model. Then when we use this multi-layer perceptron model for an image classification, what is actually going on in that particular architecture, and that is very important. So when we consider a deep neural network for classifying an image, and the problem is a 3-class problem, 3 different objects are there in the image data set. The first object is car, the second object an image containing a person, and the third that is an image containing an animal. These are the 3 different classes we are going to determine using a particular data set. As an example, if you consider a particular image from the data set, and as you know, image is nothing but a collection of pixel intensities. And in the case of a deep neural network, these pixel intensities becomes the inputs for this particular neural network. So this becomes a visible layer, and in that visible layer, we can expect the intensity values of the input pixels. Then, by considering the pixel intensities in the first hidden layer, we can extract some some features, low-level features, such as edges or straight lines, etc., etc. These type of features can be extracted in the first hidden layer. And in the second hidden layer, by considering the features extracted in the first hidden layer and combining these features, we can extract some more abstract features like corners and contours. Okay, then when we move on to the third hidden layer, again the features extracted from the first hidden layer and features extracted from the second hidden layer, these features can be combined together to generate more abstract features such as object parts. Then any number of hidden layers we can add, and if in this particular case this is the last hidden layer, and in the last hidden layer we can generate a number of object parts, and with the help of these features like object parts, we can classify the image as an image containing a person, or an image containing a car, or an image containing an animal, and so on. So this is what is actually happening inside a multi-layer perceptron when we insert the pixel intensities to the input layer. Okay, and this working is very important in the case of a multi-layer perceptron. And what do you mean by training of a multi-layer perceptron? And this training is very important because training is nothing but training is necessary for tuning the weights, tuning the weight values. And for each training instance, the back propagation algorithm first makes a prediction, that is forward pass. That means when we, for example, if we consider the previous case, from the data set, we can consider the first image. Corresponding to that image, we have a number of pixel intensity values, and these pixel intensity values are given to the input layer first. And when we provide that pixel intensity values to the input layer, then it goes to the second layer, that is the first hidden layer. Then it goes to the second hidden layer, then third hidden layer, and so on. And as a result, at last we get a particular output. And that type of an information flow is known as the forward pass. And then as a result of this forward pass, we get a prediction. Then using that predicted value and the actual value is available with us as a label of that particular data set. Then by considering the predicted value and the actual value, we can measure the error. Then goes through each layer in reverse. After calculating that error, we traverse in backwards, goes through in each layer in reverse to measure the error contribution from each connection. Contribution from each connection. Each connection means each hidden layer, and that pass is known as the reverse pass. Then finally, slightly modify the connection weights. As I said earlier, in between every layers, we can expect a number of connection weights or parameters, or these parameters are actually known as model parameters or weight values. And that is after computing the error in each layer, we can slightly modify the connection weights to reduce the error, and that error, that process is actually known as gradient descent step. Okay, but here after generating the prediction, we can measure the error, and we can back propagate this error to modify the weight values lies in between each layer. Okay, but here this process can be continued until the weights are stabilized. That is, the weight values are stabilized. That is, without when we provide a particular input many times, if the weight values are not changing too much, at that time we can stop the process. So this process is continued until we get such a situation. And at that situation, if we collect the weight values, and with the help of these weight values, we can take, or we can make a correct prediction regarding that particular input. And this process is actually known as training a multi-layer perceptron. Normally, a multi-layer perceptron is used for classification. There are, I think all of you are aware, there are two types of problems: classification problems and regression problems. And at the end of this particular lecture, we can discuss about the regression problem. Normally, multi-layer perceptron is used for classification. And when the classes are exclusive, example, classes 0 through 9 for digit image classification. That means, for example, handwriting digit identification problem. And in that case, we have 10 different classes. Classes representing the digit 0, that is the first class, another class representing the digit 1, and so on. Okay, 10 classes are there. And in that case, the output layer is modified by replacing the individual activation functions by a shared softmax function. And this is the format of that shared softmax function. Softmax of zi is equal to e raised to zi divided by sigma over j e raised to zj, and where z is the vector containing the scores of each class for the instance x. That means here it is a 10 class problem. Then in the output layer, corresponding to the first class, we have a score. Corresponding to second class, we have a score. Similarly, corresponding to the 10th class, we have a score. That means 10 different scores are there, and these scores are stored in a vector, and that vector is actually known as z. And in that vector, if we consider the ith component or ith location value, and that ith location value actually corresponds that the instance then this softmax of zi is nothing but the chance of instance x being included in the ith class. That chance can be computed with the help of softmax of zi. So softmax of z1 actually represents the probability corresponding to the first class. Softmax of z2 that represents the probability corresponding to the second class, and so on. Okay, actually softmax of zi can be considered as a normalized value, and that normalized value is nothing but a probability value, and with the help of that probability value, we can determine the involvement of the present input to that particular class. And when we include that softmax activation function along with the multi-layer perceptron model, and this is the architecture: input layer, then hidden layer, then the output layer, and in the output layer, the output of individual neurons can be passed to the activation function softmax. Then as a result, we get a probability value for each output. That means if this is the first class, and if the probability value generated at that particular neuron is 0.7, means there is a 70% chance that the input provided at that instance belongs to the first class, and that is the interpretation. And in the case of a softmax function, the output of each neuron corresponds to the estimated probability of the corresponding class. And this architecture is an example of a feed-forward neural network, or a deep neural network, or FNN. And then when an MLP or multi-layer perceptron contains 2 or more hidden layers, then such an MLP is known as a deep neural network or DNN, and this is the general architecture of a deep neural network. And this is the input layer. Input layer contains the number of features available in our data set. This is the first hidden layer, and this is the second hidden layer, third hidden layer. Any number of hidden layers we can add in this multi-layer perceptron, and at last we have a dedicated layer, and that layer is actually known as output layer. And this is the general architecture of a multi-layer perceptron. Then next, we can move on to the concept of recurrent neural networks, because in order to understand the basic architecture of a recurrent neural networks, we need the information regarding and what is the concept of a neural network and what is the concept of a deep neural network, and that information is very important to understand the concept of a recurrent neural network. And all of you know, humans don't start their thinking from scratch every second. And because we understand things based on the past experience. As an example, we can consider a simple example like this. Consider the decision regarding the items for tomorrow's breakfast. And that is mainly based on the items of today's breakfast and the items of previous days, items available in our previous days. Okay, based on that, we can take the decision regarding and what will be or what items we have to include in tomorrow's breakfast. And traditional neural networks can't do this, because it is in traditional neural network there is no facility available to memorize the informations or previous informations. And this is the it seems like a major shortcoming, or there is a limitation of the traditional neural network. And in order to address this issue, we can modify the traditional neural network, the architecture of a traditional neural network, and the resulting architecture is actually known as recurrent neural networks. And actually, recurrent neural networks means they are neural networks with loops in them and allowing information to persist. That means we can store the previous information along with the current information. And that facility, when we incorporate along with the deep neural network or a neural network architecture, then that architecture becomes a recurrent neural network. So a recurrent neural network looks very much like a feed-forward neural network, except it also has connections pointing backwards. Connection pointing backwards means to use the previous information for processing. And that means in the deep neural network or in the multi-layer perceptron, if we include such a connection, the architecture is known as a recurrent neural network. That means in the case of recurrent neural network, they have a facility to use the previous output to the at the time of processing the current input. And we can consider the simplest possible RNN composed of just one neuron. Just a minute. Hello, sorry for the interruption. Okay, we can continue. Hello.
Okay, sir, you can continue.
Okay. And consider the simplest possible recurrent neural network composed of just one neuron receiving inputs, producing an output, and sending the output back to itself in order to use it while processing the next input. That means over here, this is the architecture. Over here, this is the present input. And when we give that present input to the neuron generally generates an output. And for the next processing, this output is given to the input. That means when we unroll this particular representation, we get an architecture like this. But here, this is one neuron. And when we provide the input at the teeth instance, that is at that teeth instance input can be represented as x of t. Then as a result, we get the output as y of t. But in order to generate this y of t, we take the input from the previous time step. That is yt minus 1. Yt minus 1, that is the output obtained in t minus 1th time instance. And that output becomes the input at the time of processing the time at the time t. And when we compute the output at time t minus 1, and this is the input at the present input at the time t minus 1. And while processing that particular input, we can make use of the previous output. Previous output is yt minus 2, and this yt minus 2 becomes an input at the time of processing xt minus 1. Then as a result, we can generate yt minus 1. And this type of a processing, it is possible in the case of a recurrent neural network. That is, previous information can be used for processing the present input. So at each time step t, and this time step is also called frame, the recurrent neuron receives the input x of t, as well as its own output from the previous time step, and that output is nothing but y of t minus 1. So in order to process x of t, we need the previous output, and that previous output can be represented as yt minus 1, yt minus 1. This can be considered as a layer of recurrent neuron. And in that particular recurrent neuron, we can include any number of neurons. There is no limit for that. And when we provide this input together with the previous output, we can process all these neurons and generate the output. So when we unroll that particular architecture, we get an architecture like this. That is x of 0. Then we get y of 0. Then in order to process x of 1, that is the input corresponding to the time frame 1, we can make use of y of 0, that is previous output. Then as a result, we get the output corresponding to the time frame 1. Then this output can be used for processing the input corresponding to the time frame 2 and so on. And this type of a processing is actually happening in the case of a recurrent neural network. So each recurrent neuron has two sets of weights. From that particular architecture, it is very much clear. For each neuron, two sets of weights. One for the input x of t, that is the present input, and that weight can be represented as wx, and the other for the output of the previous time step, that is yt minus 1, and corresponding to that previous output, we actually use an entirely different set of weights, and that weight values can be represented as wy. So the output of a single recurrent neuron is actually that y of t. Y of t can be computed like this: phi of x of t transpose wx plus yt minus 1 transpose wy plus b. That is x of t, that is the present input, and this is an input vector, right? So then this is actually a matrix operation, and this is the input, and this input is nothing but the previous output. That is also a vector. Then this is another vector multiplication plus b, and this so instead of that w1 x1 plus w2 x2 plus etc plus wn xn in the case of a single perceptron model, we have a computation like this, and this value is passed to the activation function, and here phi becomes the activation function. And this can be simplified in this way. That means as a matrix operation, we can perform the operation in this way, that is phi of xt yt minus 1 dot w plus b. So, and w is another matrix, and that matrix is nothing but wx wy. Okay, and this is the mathematical representation of what is actually happening inside a recurrent neural network. Then training in recurrent neural network, that is also very important, and we can think recurrent neural network as a layered feed-forward network with shared weights, and then train the feed-forward net with weight constraints. Okay, as in the case of deep neural networks, after generating the prediction, we can compute the error, and this error can be back propagated to tune the weights. And the same process can be applied in the case of a recurrent neural network. But here, that algorithm is actually known as back propagation through time, or BPTT. And that is the training algorithm that can be used to update the weights in recurrent neural networks. So in order to update the weights corresponding to x of t and weights corresponding to yt minus 1, then in order to update these weights, we can use a learning algorithm or a training algorithm, and that algorithm is actually known as back propagation through time. And back propagation through time is normally applied to sequence data like a time series. That means a time series data. Time series data, what is actually a time series data? A timestamp is always there along with every record of a particular data table. A time frame is there. That is during time t, this is the inputs. During time t plus 1, these are the input values. During time t plus 2, these are the input values, and so on. So every instance, we have a timestamp, and that type of a data set is actually known as a time series data. And this back propagation through time is usually applied for processing time series data. And the algorithm is present a sequence of time steps of input and output pairs to the network. That is at a particular time period t, we have some input values and the corresponding output, and these input values are presented to the network. Then unroll the network, then calculate and accumulate the error across each time step. That means for each time step we have inputs. These inputs are simultaneously feed into the network. Then as a result, we can generate some outputs. Then we can roll up the network, and based on the error generated after roll-upping this network, we can back propagate that error to modify the weight values. And that type of an algorithm or that type of a training is actually happening inside the recurrent neural network, and the training algorithm is known as back propagation through time. Then now we can move on to an efficient architecture of a recurrent neural network, because in recurrent neural network we can use only the just previous output, and that is a limitation of the recurrent neural network. And in most of the time we need some other informations, or in order to use the just previous output, we have to use 2 days before information to process the current input. In that case, an architecture like RNN is not suitable that type of a processing. Then in the long short-term memory, that particular limitation of a recurrent neural network can be eliminated. Okay, so LSTM network is a recurrent neural network that is trained using back propagation through time. Same algorithm can be used for training the LSTM network. LSTM is nothing but long short-term memory, and overcomes the vanishing gradient problem. You know, I already discussed about that gradient. For example, if y is equal to x squared, consider that particular function, then what is the derivative of y with respect to x? The first derivative dy by dx in that case is 2x. Once again, if we differentiate that function, we get 2. Okay, then third time, when we differentiate that particular function, the differential coefficient becomes 0. Okay, that means when this differential coefficient vanishes, the weight updation does not happen in a particular neural network. And that is a very serious issue in the case of recurrent neural networks or deep neural networks. And that type of problem, that limitation can be very effectively handled in the case of long short-term memory by introducing some other activation functions like tan, h, sigmoid, etc. And this network, long short-term memory, is possible with the help of this particular network. It is possible to create large recurrent networks. Because we can eliminate this vanishing gradient problem. So any large type of networks can be generated with the help of long short-term memory. That is, it is possible to create large recurrent networks. Then instead of neurons, LSTM networks have memory blocks that are connected through layers. That is, in addition to the basic neurons, this LSTM networks also contains some memory blocks, and that is the main difference between the architecture of a recurrent neural network and the architecture of a long short-term memory. In addition to the basic neurons, we can add some memory blocks. And a block has classical neuron components. Inside a block, we can expect some classical neuron components plus some memory for recent sequences. Some memory so there to store the information. And a block that manages the block state and output. A block contains gates, and the responsibility of these gates and the output. A block operates upon instant input sequence, and each gate within a block uses the sigmoid activation units to control. That is, a base input sequence. Each gate within that block contains a number of gates, and inside that block, sigmoid activation function is used. Sigmoid activation function. I think you are familiar with that sigmoid activation function, because for a sigmoid activation function, the mathematical equation is 1 by 1 plus e raised to minus x. And there is an S-type function. When we plot that function, we get an S-type curve. Okay, and there is an efficient activation function in most of the cases while working with neural network. In most of the cases, we use this sigmoid activation function because to generate the gradient, it is very simple in the case of sigmoid activation function, because the derivative is nothing but x into 1 minus. Operates upon an input sequence, and each gate within a block. That block contains a number of blocks, uses the sigmoid activation function to control whether these gates are triggered or not, whether these gates are triggered or not, as in the case of our ordinary flip-flops, whether these gates are triggered or not, and any change in the state of the block. Any change, is there any change in the state of the block? If we have to make a modification in the current status of the block with the help of this sigmoid activation function, or with the help of that gate network, we can perform that modification. And also add any new information and allow this new information to flow through the block. That is, in order to preserve a particular information in that block, and with the help of this activation function and the gate network, we can do that. And all these activities are performed conditionally. That means here a number of different operations are simultaneously happening inside an LSTM block. These are the operations, whether these gates are triggered or not, any change in the state of the block, is it possible, or add any new information and allow this new information to flow through the block, and all these activities can be controlled with the help of this sigmoid activation function. And all these activities are performed conditionally. There are three types of gates within the unit. Within a LSTM block, we can expect three different types of gates. The first gate, that is known as the forget gate. This forget gate conditionally decides what information to throw away from the block. And the second gate is input gate, conditionally decides which values from the input is used to update the memory state. From the present input, what information we have to use for update the current memory state. Then output gate, that is conditionally decides what to output or generate based on the input and the memory of the block, based on the current input and the present status of the block, that is memory, what we have to generate, and that is actually decided by the output gate. Each unit is like a mini state machine where the gates of the units have weights and are learned during the training process. As in the case of our recurrent neural network, each unit is like a mini state machine. A number of gates are there where the gates of the units have weights. Each gate has its own weights that are learned during the training process. That means with the help of that back propagation through time, we can tune these weights. We can tune these gates. And this is the general architecture of a long short-term memory. General architecture of a long short-term memory. This is the present input, that is x of t, and the previous output that is h of t minus 1. And these are the only two information in the case of recurrent neural network. But in the case of LSTM cell, in addition to these two information, we have some gate networks. There is input gate is there, output gate is there, forget gate is there. And FC is nothing but the fully connected layer, that is a deep neural network. But here, when we consider f of t that corresponds to the forget gate, but here the input x of t and the previous output h of t minus 1, these two informations are connected to this particular fully connected layer, and so it is a responsibility of this fully connected layer to identify what are the different informations we have to throw away from the block. Okay, so that is the reason why this information is known as the or that gate is known as the forget gate, and we can each gate we can explain the next slide. And this operation, that is the element wise multiplication, as in the case of our w1 x1 w2 x2 w3 x3 etc., then plus represents the addition. Then this logistics, this colored portion here in each fully connected layer we have some activation functions, and this colored activation function represents the sigmoid activation function. Sigmoid activation function is also known as the logistic activation function, and this blue color that represents another activation function, and that activation function is known as the tanh activation function. And the tanh activation function is the main reason for eliminating that vanishing gradient problem in the case of long short-term memory. So this architecture is very important. While processing, we get h of t, that is the output, Then C of t, that is the long-term state. C of t can be considered as the long-term state, and this Y of t becomes the current output. And H of t and Y of t, these are same. Okay, and we can here the LSTM cell looks exactly like a regular cell, except that its state is split into two vectors, H of t and C of t, and C stands for cell, and C actually represents the memory. We can consider H of t as the short-term state and C of t as the long-term state. And there comes the main difference between the recurrent neural networks and the long short-term memory. So long-term state can be incorporated at the processing in the case of LSTM. The key idea is that the network can learn what to store in the long-term state, what to throw away, and what to read from it. And all these operations can be simultaneously done inside a long short-term memory. The key idea is that the network can learn what to store, what information we have to preserve in the long-term state, and what to throw away, that is unwanted information we can throw away, and what to read from it, what information we have to read from the long-term state and the present input to output. And all these operations can be very efficiently done within LSTM. The long-term state CT-1 travels the network from left to right, and CT-1, that is C of t, actually represents the short-term state. It first goes through a forget gate. That C of t-1 goes through a forget gate first, dropping some memories, that is unwanted memories, and then it adds some via the addition operation. That is this new information actually obtained from the present input and the previous output. So by analyzing this information, I can identify what is the information to be preserved, and that can be added along with CT-1, and unwanted information can be eliminated from CT-1. Okay. So at each time step, some memories are dropped and some memories are added. Some memories are dropped and informations are dropped, and the necessary informations are preserved. After the addition operation, the long-term state is copied and passed through the tanh function, and then the result is filtered by the output gate. The output gate, that means it is the responsibility of the tanh function to generate the actual output, and this produces the short-term state H of t. This produces the short-term state H of t, and this short-term state H of t is equal to the cell's output for this time step. That is the output. What will be the current output obtained from this G of t is partially stored in the long-term state. Okay, but here unwanted information can be eliminated, and the necessary information can be stored in the long-term state. And in order to identify the necessary information, we can make use of G of t. The three other layers are gate controllers. Three other layers are there, and these are the gate controllers. Their outputs are fed to element-wise multiplication operations. Element-wise multiplication operations, that is the element-wise multiplication operation is nothing but W1 x1 plus W2 x2 plus etc. And that is actually happening inside the perceptron model. And if the output of that network is 0, they close the gate. They close the gate, that is nothing will flow. And if the output is 1, they open it. So the forget gate, and that is the first gate, that is controlled by f of t, controls which parts of the long-term state should be erased. Which part of this is CT-1. From this CT-1, what are the informations to be eliminated? What are the informations to be eliminated? And that is actually determined by the forget gate. Okay, forget gate. So the forget gate, that is controlled by f of t, controls which parts of the long-term state should be erased. The input gate, that is controlled by I of t, controls which parts of G of t should be added to the long-term state. So input gate is responsible for identifying those parts of G of t to be added to the long-term state. And the output gate that is controlled by O of t controls which parts of the long-term state should be read and output as at this time step both to h of t and y of t. That means what becomes the output corresponding to that particular LSTM block, and that is actually determined by O of t. So the output gate controlled by O of t controls which parts of the long-term state should be read and outputs at this time step. And it goes to h of t and y of t. H of t and y of t are same. H of t represents the short-term state, and y of t represents the current output. So an LSTM cell can learn to recognize an important input, and that is the role of the input gauge. Okay, that is actually done by G of t, and store it in the long-term state. With the help of f of t from the input gate. The necessary information we can store in the long-term state. Learn to preserve it for as long as it is needed, and that is a role of the forget gate. And that information, up to what time we have to preserve that information, that is actually decided by the forget gate. And learn to extract it whenever it is needed. That is at what time we have to extract the necessary information, and that is also that is actually controlled by O of t, and that's also a responsibility of an LSTM cell. So these are the different functions happening inside long short-term memory. So we can drop some information, we can add the necessary information, we can pass the generated information, the actual information as output. All these activities can be done simultaneously. And these are some mathematical operations for generating all the necessary information, because a number of different operations, I of t, f of t, o of t, g of t, c of t, y of t, all these operations, mathematical functions for mathematical operations. So matrix operations are there, and these are the mathematical representation of all these matrix operations. And here wxi, wxf, wxo, wxg are weight matrices of the 4 layers of their connection to the input vector xi, corresponding to the input vector xi and the gates. We have some weight values, and these are the weight matrices. Then corresponding to the previous state h of t minus 1, and for the 4 different gates we need some weight values, and these are the weight values corresponding to the previous output. Then these are the bias values bi, bf, b0, bg, because you know what is the linear operation is happening inside the long short-term memory, or any perceptron model, because linear operation, you know, y is equal to mx plus c. And that C represents the y-intercept, and this y-intercept is actually known as the bias term. And here we have 4 networks, so 4 bias terms we need for processing, and these bias terms are bi, bf, bo, bg. Okay, then TensorFlow, that is actually the a high-dimensional vector, initializes bf to a vector full of ones instead of zeros to prevent in bf. Instead of initializing this b value or the bias value with 0, we can make use of ones for initialization to prevent everything will be 0 at the beginning of the training, because otherwise all the values becomes zeros. And then in order to handle that particular issue, we initialize that vector with 1. Then now we can make use of this particular constructor, that is LSTM constructor, to solve a real life problem. And this is the real life problem. The problem is actually it is a regression problem, because a numeric value is generated as a result of this particular LSTM model. So the problem can be considered a regression problem, and this problem is a regression problem to determine the number of COVID-19 confirmed cases in a day. So in the next, that means given the total number of confirmed cases in a day, starting from, for example, in this particular case, I'm going to take the data from 31/2020 to 27/2020. Okay, the task is to predict the number of COVID-19 cases in, for example, 21/7. That is up to this information, up to this date, the necessary information is available. And I think all of you know our Chief Minister's press conference every day is there, and in that press conference we have the information regarding how many patients are affected, how many COVID cases are reported in Kerala today. Then in previous days also this information is available. All these informations are available in the internet. We can access or freely download all this information, and I just downloaded the information from 31/2020 to 27/2020, and my objective is to predict, based on this information we have to predict how many COVID-19 cases we can expect in the next day. Next day is nothing but 21/7/2020. And in this present data set, the data contains 174 observations. 174 observations, and this is the format of the data set. This is a snapshot of the data set I collected for implementing this particular architecture in 31/2020. January 30, we have only one confirmed case. Then 31st, one confirmed case. Then February 1st, we have 2 cases. Then 2nd February, 3 cases, and so on. And the last entry is 27 July 20. We have 12,480 patients are there. So this data, that is a time series data, right? This is the first day, second day, third day, fourth day, etc., etc. 174 days information is there. And as a first step of building the network, we can load this data set easily using the pandas library. In Python, some libraries are there, and these libraries are freely available. And what are the various libraries needed for implementing that, we will discuss later at the time of implementing the model. But here we can load this data set easily using the pandas library. That is, in order to load this data set, after downloading the data, we have to load that data into a program, and there are some facilities already available in pandas library. And we are not interested in the date, given that each observation is separated by the same interval of 1 day. So in that case, in the case of a time series data, after getting the data, there is no importance for the date. Therefore, when we load the data set, we can exclude the first column. So when we consider the CSV file, we have 2 different columns. First is the date column, and the second is the number of confirmed cases. Once loaded, we can easily plot the whole data set. We can just plot the data set, and when we plot the data set, and what is the shape of that curve, that we will we can plot the that plotting operation can be done with the help of a facility available in Python that we will discuss later at the time of implementing the program. Now, write a simple function to convert our single column of data into 2-column data set, because actually LSTM can be considered as a supervised machine learning model. Supervised machine learning model. Then, in order to work with that supervised machine learning model, we require a labeled data set. A labeled data set. But in this case, it is a time series data. That is not a labeled data set. So it is our responsibility to convert this time series data into a labeled data. So here I am going to convert this time series data into a labeled data containing 2 columns. 2 columns. The first column containing this day's, that is patients count. This day's patients count, and the second column containing the next day's, that is T+1, that is patient count. Hello.
Hello, sir. Hello.
A disturbance. Hello.
All the attendees, please mute yourself.
The second column containing the next days, and that next days, that is T+1's patient count. That is the label in this case. The teeth patients count. That is the feature. That is the first column. and the second column information is nothing but the next day's patient count. Participants, please mute your. Hello. Hello.
Hello. Attendees, please mute yourself.
Hello.
Sir, is it audible?
Yeah.
Okay, sir, you can continue.
The function takes two arguments. That is, in order to convert this time series data into a labeled data set, I'm going to use a user-defined function. And this user-defined function takes two arguments. The first argument is nothing but the data set, which is a NumPy array that we want to convert into the data set, and that NumPy array is nothing but the time series data. Then another argument is look back, and which is the number of previous time steps to use an input variables to predict the next time period. And in this case, the default value is 1. In this case, the default value is 1. So look back actually represents the number of previous time steps. If look back is equal to 2, we can use previous 2 time steps to predict the next time's data value. And if the look back is equal to 3, then we can make use of 3 previous time steps to predict the next time period data. Okay, but in this case, the default value is 1. That means to compute the tomorrow's value, we can consider today's value. Okay. So this default value 1 will create a data set where X is the number of patients at a given time t, and Y is the number of patients at the next time, that is t plus 1. So this can be when look back is equal to 1, this particular function will generate a labeled data containing two columns. Intense disturbance is there. Hello.
Sir, sorry for the interruption.
Yes.
I think some of the attendees forgot to mute.
Okay.
You can continue, sir.
Okay. This is the user-defined function. Okay. This is the user-defined function that is to convert an array of values into a data set matrix. That is a labeled data set can be generated with the help of this particular function. Def create data set comma look back is equal to 1, and this default argument, and the default value is 1. That means at the time of calling this particular function, if this argument is missing, then it takes the value of that argument as 1. Then data x comma data y, these are two matrices. For I in range, length of data set means how many instances are there, minus look back minus 1. A data set of I from I to I plus look back comma 0. That many values we can take, and it can be stored in the array A. Then this array is appended along with data x, that is data x dot append of A. Okay, that means if look back is equal to 2 previous time steps can be, and the these 2 time steps can be treated as an array, and this array is appended to the data x. And data y dot append, that is data set I plus look back comma 0. That means the next time step. If look back is equal to 2, then the third time step, accessing the third time step, we can consider this particular syntax. Then accessing that value, it is appended along with data y. And after processing all the instances of the data set, we can return this data x and data y. So data x, in data x, that data x can be considered as a matrix containing all the independent variable values. All the independent variable values means feature values, and data y contains the label. The data y actually contains the label. So data x plus data y actually generates a labeled data set. So from the time series data set, we can generate a labeled data set with the help of the create data set user defined function. And the arguments are very important. We will discuss later regarding the calling of this particular function. And when we apply that particular function and look back is equal to 1, this is the format of the data table generated x, y. By x, here look back is equal to 1. In a particular time, the value of the total number of COVID-19 patients, that is 112, and in the next day, it becomes 118. Okay, and this value becomes the current input for the next information, that is 118 becomes the x value for the next instance, then the third data value, that becomes the output in that case. Then this third value becomes the input for the next instance, then fourth value, that is 129 becomes the output in that case. In that way, we can formulate the time series data. So this data set can be considered as a labeled data set, and these are the features or independent variables or predictors, and these are the dependent variable value. And this type of a matrix is necessary for processing using LSTM, because LSTM is a supervised machine learning algorithm. Then let's use this function to prepare the train and test data sets. Train and test data sets for modeling. In order to train the model, we need a training data set, and in order to test the performance of that model, we need a test data set. And here, so from after generating the data in XY format, we have to generate the training data and test data from that particular data set, transform data set, and for that look back is equal to 1, and in this case look back is equal to 1, or you can take look back is equal to 2, look back is equal to 3, any value can be used for this look back. Train x comma train y, create data set, train comma look back. But here create data set, this training data we can generate from training data, we can generate from this particular transform data set, and for that we can make use of create data set, train comma look back. Then so with the help of this create data set, with the help of this particular parameters, train comma look back, and here in the create data set user defined function data set, that is the data set we have to convert into this format. So here we have a data set train, and suppose we have to convert that data set train into XY format. So all the x values are preserved in train x, and y values are preserved in train y. And similarly, to generate the test data, same create data set function can be used. But here, this is the test data used to convert into XY format. That means this is a time series data, and that is a portion of the actual data set. But here, train can also be considered as a portion of the actual data, because 70% of the actual data set we can treat as a training data. And initially, the training data is a time series data, and we can convert the training data into supervised form, and in that labeled data set, the features are train x, and the labels, that is train y. Similarly, in the case of test, okay, test x, test y. Then the LSTM network expects the input data x to be provided with a specific array structure in the form of samples, comma, time steps, comma, features. Because in order to work with this LSTM, this matrix here train x can be considered as a matrix. Train y is also considered as a matrix. So this matrix and that data structure we have to modify, because LSTM work with a tensor. And so that a specific array structure we have to change in this format, that is samples comma how many samples are there, time steps, but time step or look back is equal to 1, we have only one time step. Look back is equal to 2, we have two time steps. Then how many features, how many features are there? If time step is equal to 2, 2 features are there. If time step is equal to 3, 3 features are there. And in that format we have to convert. Currently our data is the form samples comma features. How many samples, that is instances, how many features. So for example, data set is in this format 50 by 2, 50 by 2. So 15 instances are there and 2 features are there. And that is the current status of the data, but we have to convert that data set into this format. So we can transform the prepared train and test input data into the expected structure. That means expected structure is this structure using numpy.reshape, and this another functionality to convert a data with this particular structure to this particular structure. Okay, and for that we can make use of a statement like this: trainx is equal to numpy.reshape trainx. We can convert that data into this format. Trainx dot shape of 0. Shape of 0 will give the number of instances in trainx. Number of instances in trainx, comma 1, because time step is 1. Then trainx dot shape. How many features are there? How many columns are there in trainx? And that can be accessed with the help of trainx dot shape of 1. So the structure of that data set can be changed with the help of reshape. Similarly, text x can also be changed with the help of the same reshape function. So we are now ready to design and fit our LSTM network for this problem. That is, after this conversion, only we can use this data set for LSTM. Otherwise, it is not possible to use the data set for constructing the LSTM network. And the network has a visible layer with one output, because we have only one input, one output, that is y value. We have only one y value, but for another implementation, we need two output values. It is possible to generate two output values, no problem for that. Okay, but in this present implementation, we have only one input and one output. But here, the network has a visible layer with one input, a hidden layer with 4 LSTM blocks. That is, if we consider an LSTM block, inside that LSTM block, how many neurons, how many LSTM neurons are there? 4 neurons are there, and an output layer that makes a single value prediction. And that is the general structure of the LSTM network. But in the actual implementation, I would like to use an entirely different architecture to get a better performance for my model. The network has a visible layer with one input, a hidden layer with 4 LSTM blocks or neurons, and an output layer that makes a single value prediction. And the default sigmoid activation function is used for the LSTM blocks. And the network is trained for 100 epochs in this case, and a batch size of 32 is used. And I think all of you are familiar with the term epochs, how many iterations we have to perform to get the output, and that we can decide. And here I am going to use 100 epochs. And actually I am going to use a batch processing strategy, and in each batch I am going to provide 32 instances. So that is the batch size. And this is the model construction. And this construction is very important. Model sequential. Actually, I'm going to create this model with the help of the functionality available in Keras. Okay, and in Keras there are two different types of models. The first model is known as the sequential model, and the second model is known as the functional model. I don't want to discuss anything related to the functional model right now. Presently, I'm going to use the sequential model. Sequential model means in a deep neural network or in a LSTM network, different layers are there, and these layers can be sequentially connected automatically if we select the sequential model. So model.add, LSTM with 4 neurons, So this first parameter actually represents how many LSTM neurons we have to include in that particular layer. Then input shape is equal to look back comma 1. That is this actually act as an input layer, and input layer this particular network expects how many inputs, and that information we have to pass through the network through input shape. Input shape is equal to look back comma 1. Look back, if the value of look back is equal to 2, then 2 comma 1, that is 2 inputs. 2 by 1. 2 by 1 means in a row 2 inputs are there. Input shape is equal to look back comma 1. I think there is a change in this particular information. 1 comma look back. That means in each row we can expect 2 inputs. If look back is equal to 3, in each row we can expect 3 inputs. Okay, so I think it is 1 comma look back. Okay, that is the shape of the input. But in the present scenario, look back is equal to 1, so we provide 1 input, and this input is passed to the 4 LSTM neurons. And so in order to add this layer into the sequential model, we can make use of this particular statement, model dot add LSTM 4 neurons. You can use any number of neurons. Instead of 4, you can use 5, 6, or 7. Any number of neurons you can use, no problem for that. LSTM4 input shape is equal to look back 1 comma look back. Okay, then next layer, that is model dot add dense of 1. And in this particular model, this dense layer actually represents the output layer, and in the output layer we expect only one output. Therefore model dot add dense 1. But this is actually the model constructor. Instead of this model, you can add any number of LSTM layers, no problem. After this model dot add LSTM 4 input shape is equal to look back comma 1. After that we can add one more LSTM layer, and for that you just add a statement like this, model dot add LSTM, then for example LSTM 8. So we can add an LSTM layer, a new LSTM layer, as a hidden layer consisting of 8 neurons. And in that case there is no need of providing this information. Input shape is equal to look back comma 1, because this input information is provided because this layer actually acts as an input layer. Then once this input layer is defined, after that we can add any number of layers without any restriction. And how many neurons we have to include in that particular layer, that is actually determined by how many instances are there in our data set, how many features are there in our data set, and how many outputs we have to generate. And based on that we can optimize the number of neurons to be added in the LSTM layer. Then after building that model, this is our model. After building that model, the next step is to compile that model, and for that we can make use of a dedicated method, and that dedicated method is actually known as model.compile. Then inside this compile method we have to provide 2 very important information. Some other informations can also be added or provided in the compile method, but these are 2 very important information. Loss, mean squared error, that means we have to specify the loss function, in which way we have to compute the error, and that loss function we have to specify, along with a method for implementing back propagation. And in order to implement the back propagation, we need an optimizer function, and here I'm going to use an optimizer function Adam. A number of other optimization functions are also there, like stochastic gradient descent, RMS probe, etc. A number of other activation functions are there, and you can select any suitable optimization function to perform the back propagation. But here this is the loss function, this is the optimization function, and these 2 parameters are very important in the compile process. So once the model is built, the next task is to compile the model. And for at the time of compiling that model, we have to provide the loss function, and we have to provide the optimizer function. Then after the compilation process, the next task is to train the developed model with the help of the training data. And for that, we can make use of another dedicated functionality, which is known as fit. So model, because this is the name of our model. Model is the name of the model developed. Model dot fit with parameters. The parameters are very important. Train x, the training data x values. This is the training data corresponding by values. Epochs, how many iterations? Epochs is equal to 100. Then batch size, because batch processing is happening here. In each batch, how many instances we have to consider? You can use any number of instances in a batch. Batch size equal to 64, batch size equal to 128. Any that is depending on the memory capacity of or the GPU capability of our machine. We can add any number of batches or any number of instances in each batch. And here I just considered in a batch 32 instances. Verbose is equal to 2 means the development of the training process we can visualize. And for that, I just use this particular argument, verbose is equal to 2. So this particular statement actually train the network with the training data. As a result of training this network, we can optimize the weight values, we can optimize the performance of the model to get an efficient output. You can change the number of epochs from 100 to 200 or 100 to 250, 1 lakh, any number of epochs depending on the performance. If our model gives a very good performance even in epochs 100, then you can fix the number of epochs as 100. If the performance of my model is not satisfactory with this 100 epochs, you can change it as 200, no problem. Okay, but the last statement actually gives the instruction to train the developed model. Once the model is fit, we can estimate the performance of the model on the training data and the test data set. And what is the performance of the model on the training data and at this same time test data. But performance of the model is actually measured by inputting the test data, because test data, there is a separate data set, and this data set is not visible at the time of training. So what is actually the performance of the model? That is actually computed with the help of the test data. Okay, and this will give us a point of comparison for new models. Okay, that is, in order to compare the performance of the model, we have to estimate the performance. And note that we invert the predictions before calculating error scores to ensure that performance is reported in the same units as the original data. That means after generating that data set in XY format, we perform a normalization process. Because the normalization process means all the data values we can convert from the present domain to another domain. And another domain, for example, in the domain 0 to 1, all the data values can be converted to values lies in between 0 and 1, and that can be considered as a normalization process. After normalizing, when we train the data and predicting the information, the data values are also in the normalized format. But in order to understand what is the actual data, we have to unnormalize it. And for that unnormalization, we have some dedicated functionality in Python, and that we will discuss at the time of implementation. Okay, but here make predictions in order to compute the performance of the model on the training data. First of all, we can predict the values corresponding to the training data. Okay, but for that we can make use of another functionality which is known as predictor. That is, when we provide training data X, the corresponding predictions can be generated with the help of the predict method. So model.predict train X. Similarly, in order to generate the predictions corresponding to test X, we can make use of model.predict test X. And then here, after the prediction, train predict will give some predicted by values. corresponding to the training data, and here predicted by values corresponding to the test data. Okay, but all these by values are in the normalized format. Okay, so we have to convert the or invert these predictions into the normal value, and for that we can make use of train predict scalar dot inverse transform, and with the help of that particular method we can convert the normalized data into the unnormalized data. And so train predict we can convert into normalized form. Train y can also be converted into the normalized form. Similarly, test predict can be converted into the normalized form. Test y can also be converted into the normalized form by using the same functionality, that is inverse transform. Inverse transform, I think all of you are familiar with the inverse transform, because f inverse, when we consider a function y is equal to f of x, corresponding to that function we will have an inverse function also. In order to normalize the data, we have to use a function, and the inverse of that function can be used for unnormalized the data. Okay. And after that, we can calculate the root mean squared error, and that is the metric I am going to use to measure the performance of the model. So train score, what is the score of the training data, and that can be computed as math.sqrt mean squared error, and that function is there. In scikit-learn, mean squared error, that is a dedicated functionality. We can include that functionality in our program. Mean squared error, train y of 0, that is the actual data, comma, train predict colon to 0, that is a colon to 0 means train predict that actually contains the predicted information. And this is the actual information. So by considering the actual information and the predicted information, we can compute the mean squared error corresponding to the training data. And that mean squared error can be printed with the help of this particular statement. Similarly, the test score can be computed with the help of math.square root mean squared error test y of 0. This is the actual data corresponding to the test data y, test data, and this is the predicted data corresponding to the test data. And by considering the actual data and predicted data, we can compute the mean squared error corresponding to the test data. So we can print the test score, and there is a root mean square error value with the help of this particular object test score. So train score can be computed and test score can also be computed. This will give us the performance of the model. And if the root mean square error is very low, that gives our model performs better. And the root mean square value is high, that means our model is not efficient to generate the required output, and that is the interpretation of this root mean square error. Okay. And finally, we can generate predictions using the model for both the training and test data set to get a visual indication of the skill of the model. That means after generating the predictions, that is training predictions and test predictions, we can visualize those predictions with the help of the plotting facility available in Python. And because of how the data set was prepared, we must shift the predictions so that they align on the x-axis with the original data set. That means in order to correctly visualize the curve of training predictions and test predictions, we have to perform some modifications in these predictions. And once prepared, the data is plotted showing the original data set in blue. So in the same graph, we can print or we can plot all this information, original data, and which is printed in blue in the experiment. The predictions for the training data set is green, and the predictions on the unseen test data is in red. That is unseen test data set means the predictions corresponding to the test data set is represented in red in color, and that is the visualization information. Now we can just discuss the implementation of LSTM using Keras library, and I need 10 more minutes to complete this particular lecture. I would like to discuss that implementation. My slides are visible to you? Hello?
Yes, sir.
Hello? Yes, sir.
But here are the LSTM implementation to predict the total number of confirmed COVID-19 patients in Kerala from previous days counts. That is the problem. And these are the various libraries needed to implement this particular activity. Import NumPy, import matplotlib. There is we can plot the different information with the help of this particular library, matplotlib. Then pandas data frame, that is in order to read the data or in order to process the data set, we need a functionality, and there is actually all those functionalities are available in pandas. And there is a dedicated functionality, read CSV, to read the CSV file. Then import mathematical operations. In order to use mathematical operations, we need another library, and that library is known as math. And from TensorFlow.keras models, import sequential. TensorFlow.keras.models, import sequential. I already mentioned what is the importance of sequential model. Then from TensorFlow.keras.layers, import dense. That is in order to generate the hidden layers in a deep neural network. We need this functionality. And from TensorFlow.keras.layers, import LSTM. Then in order to create LSTM networks, this functionality we need, and we can incorporate that functionality into our program with the help of this particular statement. From sklearn, scikit-learn, pre-processing, import min-max scaler. I am going to use min-max scaler for normalization. Then from scikit-learn metrics, import mean squared error and loss function. And in the case of LSTM network, I am going to measure the performance of the model by using mean squared error. And these are the necessary library files. And I already discussed about this particular user-defined functionality. And this function, with the help of this function, we can convert our time series data into a labeled data set. Then and fix a random seed for reproducibility. So in the case of implementation, in between each layer of the network, some weight matrices are there. And it is our responsibility to initialize these weight matrices before starting the execution. And for that, we have to use some random numbers. And these random numbers can be accessed with the help of numpy.random.seed. Seed 7 means in order to produce the same random numbers in every execution, we have to provide a seed number. Otherwise, it is not possible to generate the same random numbers in every execution of the program. Then after that, we have to load the data set. So data frame. I am going to load the data set as a data frame, and for that I can use this CSV, and this is the path name, and this is the name of the CSV file. I'm stored this data set as a CSV file. Okay, then x is equal to data frame drop data. And as I already said, date is not an important component in this particular execution, so we can drop that data, and for that we can make use of this particular statement, data frame dot drop date x is equal to 1. X is equal to 1 means a complete column, values can be dropped. Then data set is equal to x dot values, and from the data frame is nothing but a structure with the corresponding labels. We don't want any labels here. So from that data frame, we can access only the values with the help of this particular syntax, x dot values, and those values can be stored in another object, and that object is known as data set. And this data set now can be considered as a matrix, a single column matrix. Data set is equal to x dot as type float 32, because all the processing inside the LSTM is based on floating point operations. So all the data values can be converted into floating points. That is, for that we can make use of this functionality, x dot as type float 32. And x dot head, after this conversion to visualize whether the data sets are already stored in X available in X, we can use X dot head with the help of this particular statement. The first few rows of the desired data set can be printed. And this is the information printed there. 0, that is the row number. Row number 0, the value contained is 1. Row number 2, that is 1, 2, 2, 3, 3, then 4, 3, and so on. Okay, and that is the information printed that can be printed with the help of X dot head. Then next is the normalization process. As I said earlier, we have to convert all the data values into values that belongs to a particular interval, for example 0, 1. So, and for that we can make use of min-max scalar, and feature range is equal to 0, 1. That means if this is the case, all the data values can be automatically converted into 0, 1. Values lies in between 0, 1. And so for that we can make use of an object, or we have to define an object, and the name of the object is scalar, and that object is defined with the help of min-max scalar. Then all the data values can be converted with the help of this particular functionality, scalar.fit transform data set. So from the data set, all the data values are transformed into values lies in between 0, 1 with the help of this particular statement. Now, when we print the informations contained in the data set, we can see that all the values are lies in between 0 and 1. So split into, then after that next we have to generate training data and test data, and for that, as a first step of the process, we have to split the data set, split into train and test sets. So for that, first of all, we have to decide the test size, and sorry, train size, and after that we can decide the test size. Then how we can fix the train size? Int of that is integer part, length of data sets. Length of data set, how many instances are there in that data set, into 0.67. That means 67% of the data we have to consider as the training data, and for that first of all we have to consider the index corresponding to that 67%, and that index can be accessed like this, and that index is now available in train size. The remaining data and the corresponding index is now available in test size, that is length of data set minus train size, and that is the size of the test data, and that size is now available in test size. So considering these two size values, we can define our training data and test data, and train comma test. How training data can be defined? From data set 0 to row number 0 to train size, all columns. Colon represents all columns, and all these values are now transferred to train. Then data set of train size to length of data set, all columns, and the remaining columns, and that is transferred to remaining instances, that is transferred to test. So with the help of the train size and test size, we can fix the training data and the test data. But here 67% of the data contained in the original data set, that is treated as training data, and the remaining 33% that is treated as the test data. You can change, instead of, in order to generate 70%, you just provide 0.70, no problem. In order to generate 80% of the data set as training data, you just 0.80, no problem for that. And then now, actually here training data and test data, all these are time series data, and as I said earlier, we have to convert all these time series data into labeled data, and for that, for the time being, I'm going to use the look back is equal to 3. So here when we consider look back is equal to 3, and when we consider the x values, we have 3 columns are there. Okay, and 1 column for the outputs. Okay, and that type of a data set can be generated here. Train x comma train y is equal to create data set. Create data set is already used there. Train, that is the data set. I am going to convert look back. Look back is equal to 3. Okay, but here the first 3 informations we can access from the training data, and it can be loaded into trainx as the values of the three features. And the fourth feature becomes the label. Fourth feature becomes the label. And that type of an operation is actually happening inside create dataset. Similarly, test dataset can also be generated with the help of create dataset test comma look back. Then train x dot shape, and when we print the shape of this training data, you can see that it contains 111, 3, and 111, 3 means 111 instances and 3 columns. 111 instances and 3 columns. Therefore, that means train x is a matrix and how many rows? 111 columns, rows and 3 columns. And after that, we have to reshape the data sets, training data and test data. We have to reshape because LSTM work with tensors, high dimensional data sets. So we have to reshape the training data X. For that, we can make use of numpy dot reshape train x, train x dot shape of 0. Shape of 0 will print this information 111 number of instances. Train x dot shape, that is number of columns, that is 3 number of columns, then 1, that is the number of instances in each block, how many instances, and in order to store that instance, we have to add one more dimension, and that is the use of the reshape functionality. Train x dot shape of 0, train x dot shape of 1, 1, and a new dimension is added along with train x. And similarly, text x can also be reshaped in that way. And when we, after that reshaping operation, when we print the shape of the train x, we can see that 111, 3, 1. That means 111 instances, 3 columns, and right now 1 instance per batch, and that is the information. Okay, and that type of an information is needed for work with LSTM. Why we need that type of a structure for in order to work with LSTM? That is a question. You can find out the answer for that question. Okay. Then, as I said earlier, next we can create the LSTM network model sequential model.add LSTM 35. Okay, and input shape is equal to look back, 1. Then model.add LSTM of 50. But here, this is the input. This is the input layer. And what is the use of return sequences is equal to true. It is your responsibility to access the information. And what is the importance of this return sequences is equal to true. And other informations I already mentioned in the at the time of explaining the structure of the LSTM network. Then this is an input layer together with the LSTM network, LSTM layer. Okay, then one more LSTM layer I used in this particular model. So in order to add that LSTM layer, I just used model.add LSTM 50. But here 35 neurons, here 50 neurons, and model.add dense 1, because in this particular example we have only one output, and so I just use a hidden layer with 1 neuron. And here the activation functions are not mentioned. By default, it takes the activation function sigmoid. Okay, and when we print the summary of that model.summary, it prints an information like this. And these are the, but here the model summary actually displays the information regarding the parameters. How many model parameters are there? And there are 2 different types of parameters, model parameters and hyperparameters. But here, number of hidden layers, number of neurons in each hidden layer, all these are hyperparameters. Okay, and the model parameters means the weight values. And weight values are the model parameters. And here, how many parameters are there? 22,431 model parameters are there. That is, that much weight values are there in this particular implementation. That is the information corresponding to this particular statement, right? And after that, as I said earlier, we can compile. Loss is equal to mean squared error. Optimizer is equal to Adam. After that, we can train the data, train the model. And for that, we can make use of the fit method. Train x, train y. Fbox is equal to 100. Batch size is equal to 64. You can use batch size is equal to 32, no problem. Verbose is equal to 2. Then Then here after this after the execution of this particular statement, then we can see at the time of executing this particular statement, we can see some very important information such as the loss, then validity, loss generated at each stage, the mean square error generated at each epoch, and so on. These informations are displayed there when we when executing this particular statement, model.fit. Okay, and that you can visualize that. We can visualize that information, and then after that, next we have to visualize the predictions. Visualize the predictions. But here, after building the model, we can generate some predictions. And here I'm going to use two different type of predictions, and that predictions I already explained in my previous slide. The prediction corresponding to training data and the prediction corresponding to the test data. And these predictions can be generated with the help of, and that statement I think actually missing in this particular statement, that is after this we have two more statements, that is train predictor is equal to model.predict train x. That is when we use that particular statement, the predictions corresponding to train x that can be generated. Then text predict text x, text prediction corresponding to the test predictor is equal to model.predict text x. These two statements I just not a number value, and after that from look back to length of actual train predictor, and that is the training prediction, actual train prediction, and this actual train predict can be generated as model.predict train x. Okay, then there is plot the predict value in the train predict plot. Similarly, we can plot the test values in test predict plot, and for that this shifting operation can be generated there. Then we can plot, or we can visualize a plot plt.plot scalar.inverse transform data set. This is the plot corresponding to the original data set, and this is the plot corresponding to the train predict. This is the plot corresponding to the test predictor. And plt.show, when this particular statement is executed, we get a prediction like this. So this prediction gives a lot of very important information regarding that COVID-19 pandemic. But here this is the original curve, and this curve goes in this way, exponentially it goes. Okay, but when we consider the train prediction up to this train prediction, and this is the test prediction. The test prediction is also goes in this way. So when we visualize these two curves, we can see that our prediction is more or less exact, but we need some more tuning of this particular model to get an actual prediction. And that is the reason why at the beginning of the lecture I told you this is only prototype. It is your responsibility to convert this prototype into a model giving the actual prediction. There is always some information lag in this case. Otherwise, this test predict will also goes like this. But when we analyze, over here. This information can be used. For the prediction. But here, this is the prediction. Y is equal to predict. That is, when we consider the total prediction, and in order to get the actual data, I just use all the different instances for the prediction. Okay, because all the different 174 instances are now available in X. I'm going to use this X for prediction. So predict is equal to model.predict X. Okay, that means when we consider all the different data instances corresponding to all those data instances, and by using this particular model, we can generate the prediction, and all those predictions are available in predictor. Okay, and that is a one-dimensional array. And using this prediction, using that one-dimensional array, we can print and what is the next expected value. Next day, what information we have to expect for this particular or using this particular model, and that can be generated like this: y is equal to predict -3 colon comma colon. That means from the predict array, we can consider the previous three values. And these values can be considered as a matrix suitable for LSTM model, and for that we can make use of this particular statement, reshape statement. Then based on that, based on these three values, we can predict the next value. That is for that model dot predict y comma y. Okay, predict y. That is when we provide these three values, it generates the output value, and that output value is now available in next y. And when we print that next y, it generates a value lies in between 0 and 1, 0.710758, and this is the value printed there. And the actual value, the actual next y can be printed with the help of scalar dot inverse transform next y. Inverse transform, I already told you regarding the use of this inverse transform next y. So print actual next y, and as a result, we can print 8870.549. This is a numeric value. So normally the next in the next day, how many patients we can expect? That is 8,871 patients we can expect. This is not a correct value, but we can convert the model for predicting the correct value by changing some parameters, some hyperparameters we can change, some optimizer functions we can change, and these type of modifications we can done with the help of this particular model. And as a result of tuning that model in that way, we can generate the correct prediction. No doubt in that. But for the time being, it generates only an approximate value, but this value is not accurate, because the last value is 12,000 something. Normally, in the next day, 12,000 plus 3,000. That type of a value we always expect in today's environment. And that type of a value we have to generate. We can generate. It is possible by tuning the parameters of the model. Then this is another very important information. The next 10 days, what were the status of the COVID-19 patients? That can also be printed. Then using this particular model, we can generate the next 10 days information in this way. Okay, 879288. But when we modify, or after 1 month or after 2 months, what will be the status of the COVID-19 patients in Kerala, and that can be generated with the help of the model, the LSTM model. And this is a very efficient model in machine learning. And with this, I would like to conclude my lecture. And thank you all for hearing me patiently and the great support given to me during my lecture. And once again, I extend my sincere gratitude to all the faculty members of the department for giving me this wonderful opportunity to discuss with you this efficient deep learning architecture, that is LSTM. And thank you very much. Thank you very much.
Thank you, sir. Hope it was a very effective class. Now it's time for sharing. Participants, you can ask your queries through the chat box. We'll get it clarified. And we have some questions here. First one is, which one is more suitable for image classification, CNN or RNN, and why?
Image classification, we can use the convolutional neural network because all the different layers of that convolutional neural network is designed to work with the images, So CNN is more efficient compared to LSTM or RNN. And RNN or LSTM is mostly suited for time series data processing.
Okay, sir. Next question. In the case of disease prediction, which one is more suitable, CNN or RNN?
And if the disease prediction is based on some, for example, medical images, you can go for CNN. And if some clinical data values are available, using those clinical data values, DNN or RNN, you can predict, no problem. And what data is available, based on that data, we can select the model.
Next question. Do RNN take more time when compared to other models as it has a recurrent nature?
Other models means, for example, the, deep neural networks or some other machine learning models. And normally it takes a long time, but we can optimize. With the help of some data pre-processing strategies. This computation time can be reduced to a great extent.
The next question, sir. Can you point out the difference between CNN and RNN?
In CNN, there are two different types of networks. The first network, that is the convolutional part, and with the help of that convolutional layer part, we can extract the features. Our feature extraction is also part of that convolutional neural network. And after extracting that those features, with the help of a deep neural network, we can classify those features. And that is what is actually happening inside the convolutional neural network. But in the case of RNN, we can take the time series data, we can process the time series data. Okay, that in RNN feature extraction stage, and that stage is not available. We have to extract the features separately, then only we can use with RNN. But in the case of CNN, there is no need of any extra feature extraction stage.
Okay, next question. Can we use RNN for spam detection?
Definitely we can use RNN for spam detection. No problem for that.
Okay. Do the data involved in sentiment analysis belongs to time series data?
Yes, and that time series data can be very efficiently processed. But in the case of sentiment analysis, after generating the data, we can convert the data in the form of a time series data. Then we can use RNN or LSTM for processing.
Another question we have is, what is Pandas library?
Pandas library means actually that gives some functionalities to process the data frame. And for that, we have to understand the difference between a data frame and a matrix. In data frame is actually similar to our normal database files. Okay, because every row and every column can be labeled. But at the time of processing, these labels are not needed. So all the values contained in the data frame is converted into some arrays. And for that, we can make use of NumPy. Okay, then only we can process. And while printing the information, again, we can convert the array into a data frame. And with the help of the data frame, we can print the information in a meaningful way.
Next question. For this, can we use MATLAB?
Pardon?
For this, can we use MATLAB?
MATLAB. Oh, definitely we can use MATLAB. But it is the problem is it's a proprietary software. You have to spend a lot of money to purchase that, and that is the only difference. All those functionalities are already available with MATLAB also in latest version.
Okay. Our next question, can we use LSTM for natural language processing?
Oh, definitely we can make use of natural language processing. LSTM can be used. No problem for that.
Next question we have, why we need batches to build model?
Batches to build model means our most of the systems are GPU based systems. And if you analyze the architecture of the GPU, this architecture is mostly suited for high dimensional tensors. And in the case of high dimensional tensors, the data values are mapped into high dimensions, that is row, column, depth, etc. And that type of a dimension is necessary to work with GPU based systems. And then only we get the maximum performance.
Next question, for cancer detection, which algorithm will be suited well?
For cancer detection, first of all, we have to perform a segmentation first. And for segmentation, I think it is better to use UNet-like structures. Then after that, after segmenting the various regions, we can extract the features from these regions. And then for that, we can make use of a CNN or some pre-trained models we can make use of for getting the efficient performance. Some other very efficient architectures are also available. UNet, VNet, then DenseNet, etc., etc.
The next question is, what is the vanishing gradient issue in DNN?
Vanishing gradient, I already explained about that vanishing gradient issue, because after a certain epoch, the data values or the parameter model parameter values will not change. That is, a stabilized environment is there. Okay, then actually when we get a stabilized environment, but the weight values are not optimized in that case. And that type of a problem is actually known as a vanishing gradient problem, because the gradient becomes zero in a particular stage. And after that, there is no change in the weight values during the training process. And that process is actually known as vanishing gradient problem.
Okay, next question. Which one is good to improve resolution of medical colleges, RNN or CNN?
Pardon? I didn't get the...
Which one is good to improve resolution of medical images, RNN or CNN? Yes, medical images.
Medical images to improve the resolution. I think it is better to go for autoencoders. Autoencoders, another deep learning construct, and with the help of and various forms of autoencoders are there, like denoising autoencoders, then vanilla autoencoders, etc., etc. With the help of that particular construct, we can eliminate from the image unwanted pixel intensities. I think it is better to use autoencoder like structure for that.
Okay, we have one more question here. Is there any specific area where RNN performs well?
In time series data processing area, RNN performs well, because RNN is mostly suitable for time series data processing.
Thank you, sir. I think we have covered all our questions, and the participants, you can have your feedback form from the chat box. Now, coming to the end of the session, we have vote of thanks. To propose the vote of thanks, I invite the Vice Principal of our college, Mr. M.G. Vinay Kumar. Over to you, sir.
Thank you, Miss. Can you hear me?
Yeah, sir, it's audible.
Okay. Respected Chief Guest and the resource person, Dr. Sabu M.K., Associate Professor of Computer Applications Department, IQAC. Our beloved Secretary and Correspondent, Janab Nawaz Abdulla. Respected Principal, Dr. Shaji K., Head of the Department of Computer Applications, Resina Mall, and all the participants from various colleges, principals, students. This webinar was very interesting and informative, and also very lengthy also. I hope the participants utilize the knowledge and experience of the resource person well, and it is my honor and gratitude and privilege to propose the vote of thanks on behalf of our college. And first of all, I extend the sincere thanks to the resource person, Dr. Sabu MK, for educating the participants regarding the machine learning. And I think it is a very lengthy session and a very good session and a very wonderful session. And thank you, sir, for spending such a long time along with us and educating the participants. Thank you, sir.
Thank you, sir. Thank you.
And regarding the management participation, our secretary and correspondent, Janab Nawaz Abdullah was present in the webinar, and he was the backbone and supporting factor for our college, and he is also the motivating factor for college. And thank you, sir, for your spending valuable time to participate in the seminar. Thank you, sir. I express my heartfelt thank and gratitude to our respected principal, Dr. Shaji K, for the participation and guidance. I also express my sincere gratitude to Ms. Resna Mall, HOD of BCA department, for arranging and organizing a wonderful seminar like this. And I thank all the participants from various colleges and students to make this webinar a grand success. And also, the success of this webinar is the teamwork of our IQAC department and the IQAC coordinator, Tojin Jones, and the team members. And they should deserve a big thank for their laborious and valuable work to make this seminar a successful one. Thank you, all of you. Once again, thank everybody. Thank you.
Thank you, sir. With this, we have come the end of today's session. Thank you all. Stay home, stay safe. Thank you.